Hello and welcome everyone to a special edition of your Chem 233L class. So this week what we're going to do is we're going to focus on the introduction of what we call combined spectroscopy problems, where basically it's going to be a review of how to use IR and NMR to analyze compounds. So in other words, like how to analyze NMR and IR data. And then we're going to add on top of it mass spectrometry, or MS. That's what the lecture is going to be focused on here. As your lab professor, I'm going to be mostly focused on how to analyze the data. We'll go briefly through the theory behind it, but we're not going to focus on that here so much as the analysis itself for the lab class. I've thrown up the PDF for the relevant chapter from a really good textbook that I like, the Klein Organic Chemistry textbook. The chapters for both IR and NMR are there. So if you want some more information on the theory behind it, definitely read through that. The next thing that we're going to do and I forgot to mention, we're also going to briefly talk about carbon 13 NMR, which I know when I taught Chem 231 last semester, I didn't teach that carbon NMR, but we will incorporate it this semester. So I'll show you how to analyze carbon 13 NMRs as well. Once we kind of finish all of that, what we're going to do is we're going to go through, I have this like little step-by-step process to solve these combined spectroscopy problems, where by the end of it, if I give you a mass spectrum, I give you an IR, and I give you an NMR, either Proton NMR or both Proton and carbon 13 NMR, you should be able to tell me what the structural model is with reasonable limitations. Like if I give you that type of problem, you should be able to analyze those spectra and come up with a structure. So that's going to be our goal for this week. We're also going to have the data posted for experiment 1 this week, but I'm going to push the due date on that back a little bit so that we can focus on this just at the beginning. But let's go ahead and get started. So this is, we're going to start by talking about mass spectrometry, because mass spectrometry in the combined spectroscopy exercises, it's going to be the first thing that you do, that you analyze. And the reason that you do it is if you analyze the mass spectrum properly, you can determine the molar mass and the chemical formula for a compound. So basically, you use mass spectrometry to determine the molar mass. The molar mass is going to tell you what the formula is. So again, the theory, we're not going to focus on too much here, but the idea is basically you take a sample of a compound, it's vaporized, it's ionized, so it's you evaporate it, it gets hit with a beam of electrons, and then it's sent through a magnet where based on the charge to mass ratio, it'll either take a longer time to fly and hit the detector or a shorter time. So if it's a very massive compound, it's going to go farther through the magnet because it's just harder to pull. Whereas if it's a lighter compound, the magnetic field is going to have a stronger effect on its movement, so it's going to hit the detector earlier. And then based on that charge to mass ratio, you detect and graph those masses. So again, this is not what we're going to worry about here, but the idea is basically you take your organic molecule, you evaporate it, hit it with a beam of electrons, and that gives you this here, which is what we call the radical cation. Basically, by hitting it with a beam of electrons, you're going to knock one of the electrons loose, and that gives you this radical cation here. And that's what you can actually analyze using the magnetic field. Now, the good news here is if we can identify the radical cation, its mass is essentially the same as the parent, because you lose an electron, but remember, electrons don't have much mass, so it doesn't really affect the overall mass here. So if this radical cation remains intact, it doesn't always, but for most of the examples that I'm going to show you, it does. If it remains intact, then we call it the molecular ion, or more commonly, the way I'm going to refer to it is the parent ion. The reason we call it the parent is because it's from the parent compound, and that's what was produced. Now, most radical cations will fragment, where rather than staying in this unstable situation here, where you have, rather than a 2-electron bond, you have like a 1-electron bond, that's unstable. So you will fragment into a radical and a carbocation. The radicals, you won't be able to see those because they don't have any charge. And it takes a positive or a negative charge to interact with the magnetic field, right? Because magnetic fields are, they're electromagnetic. So if you don't have an electrical charge, then you're not going to interact with that magnetic field, so you're not going to hit the detector. But the carbocation, on the other hand, that's formed, that will be affected by the magnetic field, and thus it will show up on the detector. Okay. All right, and so the way that a mass spectrum looks, this is a very basic, this is a very basic mass spectrum here. It's just methane's mass spectrum. And what we notice right away is we have the base peak. That's going to be the tallest peak. That shows up at 16 mass to charge ratio. Now, if you have a charge of +1, which is going to be the most common thing for organic chemistry, then that 16 mass to charge ratio just represents basically that your parent compound, or the compound that's represented here, has a mass of 16 atomic mass units, AMU. If you do inorganic chemistry, oftentimes you'll have metals that you shoot into the mass spectrometer, and then you frequently get, fragments that have a +2 charge or a +3 charge even is possible. So that gets a little more complicated, but we're just dealing with organic chemistry this semester. So we're going to focus on this, this idea that basically what we have on the bottom here, that's going to tell us the atomic mass unit of the fragment that we're looking at here. Now, in this case, the base peak shows up at 16 atomic mass units. That makes sense. For carbon, the most abundant isotope of carbon has an AMU of 12, so carbon 12. And then hydrogen, its most abundant isotope is hydrogen 1, so that's protium. So it's 12 plus 1 plus 1 plus 1 plus 1 equals 16. And sure enough, that's exactly where it shows up. And so this parent peak is the base peak for methane. So again, we want to remember the base peak, that's the tallest one, and that one's the one that's set to 100 relative abundance. That's how you can identify what the base peak is. But it's important to note, the base peak is not always going to be the parent peak. It just happens to be in this case. So now you notice that's not the only fragment that we see, right? We also have fragments at 15 atomic mass units, then down to 14, 13, and even down to 12. So the existence of these other fragments suggests that something else is going on here. And sure enough, if you take the molecular ion that we would predict from methane and you fragment it, you get this methyl carbocation radical, or I'm sorry, not a radical, this methyl carbocation fragment that shows up at M/Z equals 15. That's a pretty good indication of like where that peak at 15 comes from, which is the second most abundant. Then you can fragment it further and break off more of these protons basically as it passes through the ionizing source. Okay, so yeah, mass spec is used all over the place. That's why we're going to emphasize it this semester and be able to analyze it. Basically, if you go into biotech, pharmaceutical companies, if there's some clinical testing that you need to do, so health work, environmental as well. So like, for example, for pharmaceutical, it's going to be important to be able to identify what compound you have. And we're going to show you a sequence of ways that you can identify a compound this semester. If you go into biotech, things like amino acid sequencing, and then also analyzing proteins. Protein analysis using mass spectrometry is pretty complicated, but it's actually extremely useful to figure out the way the protein is oriented and how it's configured, how the different things work together. As well as like in a clinical setting. So if you like analyze blood, oftentimes, so like hemoglobin, for example, is analyzed through mass spectrometry. Environmental techniques as well, like you can use mass spectrometry to test for drugs or test for contaminants in water and in food. And then even in geological forensic and many more. If you ever go to the airport and they swab your hands, this always happens to me for some reason. Maybe it's because of the beard or something, but like feels like all the time when I go into the airport, they want to swab my hands and they run it through a little machine. That machine is a mass spectrometer. And basically what they're doing is they're looking for molecules that are usually used like to produce explosives, and those give particular mass spectrum that that like they give it off. One time I was going to Indiana, and like going to Indiana, there's no good burritos there, so I brought a burrito with me, and it goes through the little baggage detector, and it's wrapped in aluminum foil. So it was immediately pulled out, and they had to swab the outside of the burrito with that mass spectrum detector. But it turns out it was just a burrito, nothing to be worried about. But yeah, just to kind of like check that out. Okay. All right. So now going a little bit further, if we look at benzene, so benzene has a peak right at 78 here, and that 78 represents the parent peak, because this benzene is very stable. Hopefully that's something you remember from last year. Benzene itself is very stable because it's got these alternating pi bonds that can resonate through the ring, and so it's not going to fragment easily. And so we end up with the fact that the parent peak is the base peak for benzene. But that's not the case for pentane, for example. Pentane fragments really easily, in fact, and you can see that rather than the parent peak, which is all the way over at 72, the base peak ends up being about halfway through, around 44. So it just tells us that basically there's a lot of ways that you can fragment pentane. And we'll look at that a little bit very briefly, but again, we're going to be focusing on the parent peaks here. So this end down here. Okay, so how do you analyze the parent peak? Remember, the M/Z for the parent ion, that's going to give you the molar mass of the compound. And there's a couple good things that we can pull right away, because good pieces of information we can pull right away because we are doing organic chemistry. If we have an odd massed parent peak, what that means is usually there's an odd number of nitrogen atoms in the molecule. Because if you go down the list of atoms that are going to be present in these compounds, it's going to be carbon. Carbon has a atomic mass of 12. Oxygen, atomic mass 16. That's going to be very common. Now, hydrogen, atomic mass 1, but in an organic molecule, you're always going to have some factor of 2 of those hydrogens. So when you add in a nitrogen, not only is it atomic number or atomic mass of 15 AMU, then it also bonds to just 2 other hydrogens. So that's 15 plus 2, that's 17. That accounts for a odd number that you actually see in the peak. And you'll see as we go through more of these that the only time you're going to see an odd number is when you have a nitrogen involved in the molecule. So it's pretty interesting. Yeah, so like for example, like if you look at 1, 2, 3, 4, 5 pentane versus aminobutane versus diaminobutane, if you have pentane that's got a molar mass of 72, aminobutane that's molar mass of 73, again because you have the odd mass from the nitrogen. Now, if you have 2 nitrogen atoms, then they cancel out, right? They're going to form a even number when you add 2 odd numbers together. So just keep that in mind. But that's one big clue here. Once we find the parent peak, if it's odd, we can guess most likely that we have either 1 or 3 nitrogens. Okay, now here's an interesting thing that also shows up. Not only do we have the parent peak, we also see that beyond the parent peak, we have a smaller peak at the M+1 range. So this is our M radical peak, and this is M+1. How can that be, right? Because this is 16, this is 17. I already said, 12, 13, 14, 15, 16. But guess what? Mass spec is so sensitive, they can actually detect individual compounds that have a particular isotope. And in fact, in this case, the reason that you see a 1% high peak at the M+1 range is because 1% of all carbon atoms are carbon 13. So in this case, 1% of all these molecules are going to have 13, 14, 15, 16, 17 as their molar mass. And that's what actually shows up here in this tiny little bit. Now what's cool is, and we're going to do this when we talk about the combined spectroscopy handout, we actually have, by comparing the height of this peak and this peak, we can determine the number of carbons that there are in our molecule. Like for here, for example, we're going to have about a 1% compared to 100%. That tells us that 1%, so 1 to 100 ratio, that's going to tell us that we have one carbon. Whereas if this were more like 2%, that's a pretty good indication that we have 2 carbon atoms. If this were 3% of this height, that would give us 3 carbon atoms. And we'll have like a specific math that you can go through and keep track of, but it's just a really good way to like figure out our molar mass and our molecular formula. Yeah, so this gives you another idea, decane basically. So decane has an M+1 peak that's almost 10%. And so this 10% basically indicates that you have a 10 carbon atoms. So that's gonna, I'll show you exactly how to do that when we get to the combined spectroscopy handout after this, but that's just kind of showing you the idea here. Okay, more information that you can get from it. So remember, the odd number is going to tell us that we probably have a nitrogen. The presence of an M+1 peak can tell us how many carbons are in our molecule. And then we have 2 other atoms that occasionally show up that give very distinctive fingerprint signals. That's chlorine and bromine. So chlorine is mostly 2 isotopes. Well, it's entirely 2 isotopes that are stable. We have chlorine 35 that accounts for 3/4 of all of the chlorine in the world. Chlorine 37 accounts for 24% of the chlorine atoms, in the world. So what we actually see is if you have a chlorine atom, and you take the mass spectrum of it, you get this M+2 peak that shows up at about 1/3 the height of the M parent peak here. So here, our parent peak shows up at 112. Then we have a peak at 114 that's about 1/3 of the height. And that's very distinctive, and that tells you right away, oh, there's a chlorine atom in this molecule. Bromine has a similar thing going on, except it's even closer. So you have bromine 79 and bromine 81. Bromine 79 is about 51% of all the bromine, and then bromine 81 is about 49%. So you get an M and M+2 peak that are almost equally strong. So here's our parent peak here at wherever this happens to be, and then just 2 atomic mass units above that, we get about an equal peak. And so that tells us basically that, oh, hey, you have bromine here. I hope that makes sense. Just kind of pointing out like where you can find, how you can kind of identify right away, oh, I see these 2 equal peaks. They're about 2 apart from each other. That's a pretty good indication that you have bromine. Okay. Yeah, so again, this is going to, you can analyze the fragments as well. Pentane fragments into an M-15, M-29, M-43, and M-57 peak. And all that's doing is basically saying you can either remove, here, let me annotate here real quick. Again, this is not crucial for this lab. You can cut off a methyl group. You can cut off an ethyl group. That's this one here. You can cut off a propyl group, or you can cut off the other methyl group. And that's what gives rise to all these different fragments here. Cutting off one methyl group is M-15. The ethyl group cutoff is M-29. The propyl group cutoff is M-43. And then you cut off a butyl group, and that's your M-57. And it kind of makes sense, right? If you look at the butyl group, I'm sorry, this is the methyl group over here, and then this is the butyl group. They kind of mirror each other a little bit. So that's just like a way to kind of check that. Again, we're not worried about that. We're going to focus on the parent peaks for this lab. Okay, let's not worry about that. Okay, so here's your fragmentation. Just so you know, you can see alpha cleavage. This is where basically an alcohol has a particular fragmentation type, where in an alpha cleavage, you end up forming either an oxonium ion or you form an alkene. So the alkene is going to show up, basically you lose the water molecule from that. It's going to show up at M-18. And then in the case of this oxonium atom, you're going to lose basically a whole fraction here. So you could either split it, here, which is what's visualized, or it could split here just in the exact same way. And that's going to vary based on it. Again, I'm not worried about that because we're going to be focusing on the parent peaks here. Oh yeah, amines also do alpha cleavage. And then you can read about McLafferty arrangement as well in the book section that I'll be putting up. But we want to focus on the parent peaks for this, this class. And yeah, this just kind of gives you an idea of what those are going to look like. Okay, so again, just sometimes it's not good enough to have like a low-res mass spectrometer. Sometimes you need high-res mass spectrometry. Basically, it uses a more sensitive detector, and it determines the mass to charge ratio up to 4 or 5 decimal places. And so this is what that looks like. Basically, you just notice, oh, there's more significant digits, and that way you can be more specific about which molecule it is. Basically, the more you narrow down that number, the fewer possible combinations of atoms can fit that number. So the more sure you can be about that molecule's existence. Yep. Okay. Yeah, and this is just kind of shoring that up. We don't actually use high-res mass spec in this lab, but when you do analysis in the future, you may run into one. So just so you know, it's a way to be more certain that you have a particular compound. Okay. Now this is something that we are going to do, which is where you're going to have data from. And so I want to explain how you're going to see this data and then how you can use it, which is you can couple a mass spectrometer to a gas chromatography instrument. And what that does is, hopefully you recall from last semester, gas chromatography, this is what it looks like, right? You vaporize a compound, it goes through the column, and then it comes out on the other side of the column, and they separate based on polarity, generally speaking, or how they interact with the column in any case. And you get these different peaks here. Well, rather than just running it through a detector, there's a detector there, but then that detector is going to link up to a mass spectrometer. So this mass spectrometer, then you ionize it, and then there's the ion sorting region, and then you have your detector, and that goes to the data system here. So rather than just having a mass spectrum of a whole sample, instead you separate out the sample into all of its components, and then you get a mass spectrum for each of these peaks here. So there's a mass spectrum representing this peak, mass spectrum with this peak, and you can identify the different components of a mixture in this way. And yeah, this is more common when you have like biological components. So things like blood and urine are often analyzed through GCMS. And then if you have, fermentation products as well. So like if you go into biotech, if you're interested in pharmaceuticals and stuff like that, oftentimes the way that they make molecules is through fermentation, where you make a bacteria have all of the proteins necessary to make a molecule, and then you're hunting for that molecule. You're going to use GCMS to analyze it. And there's a few other ways that you can do it too, but that's one of the main ways that they do it. Okay. So now, okay, finally we're at the really important part here, which is what do we use mass spectrometry for? I told you already, we figure out the molar mass. And the reason that we figure out the molar mass is because we want to find the molecular formula. So what we do is we use the mass spec to find the molecular formula. And I'm going to show you exactly how to do that when we go through the handout below. We know that we can use the IR then to determine the functional groups that are present. So that's going to give us an idea of the bonding rearrangements. And we want to figure out the full structure. So then we're going to use NMR on top of all of that. So, okay, so in order to analyze the formula, in order to figure out what kind of functional groups we could have, what we want to do is estimate the degree of unsaturation. Now, I know I talked about this with my students last semester in my organic chemistry class, but not all of you were there. So let's go ahead and briefly talk about it. The alkanes always follow this formula where you have a number of carbons, n, then the number of hydrogens has to be 2 times n plus 2. And that's just mathematically, that's how it always works out. So like pentane, for example, C5H12, n equals 5, 2n plus 2 equals 12. Now, for every pi bond or every ring that's involved, you introduce what's called a degree of unsaturation. And that's basically you're going to reduce the number of hydrogens by 2. So if you look at pentene, for example, that's 1 pi bond added in. You're going to reduce the number of hydrogens by 2. So you get C5H10. Now, pentyne, introduces 2 pi bonds. So what happens there is you lose 2 times 2, 4 hydrogens. So the new formula is C5H8. The degree of unsaturation for pentene is 1. The degree of unsaturation for pentyne is 2, because you have 2 pi bonds. And again, this is what we mean when we say unsaturated compounds. So if you look at C4H6, for example, C4H6, you know that an alkane with 4 carbons should have C4, H, and then do this 2n plus 2, 10. So you're missing 4 hydrogens. Missing 4 hydrogens means you have 2 degrees of unsaturation. 2 degrees of unsaturation means you can either have 2 pi bonds, or you could have a ring and a pi bond, or you could have 2 rings. So here are the possible isomers just based on that. 2 double bonds, 1 triple bond, right? Because that's 2 different pi bonds. 2 rings, this is a highly unlikely, highly unstable molecule, but you can draw it, right? And then you could also have a ring and a double bond, which these are the possibilities there. So 1 degree of unsaturation equals 1 unit on the hydrogen deficiency index. This hydrogen deficiency index is basically going to tell us the number of degrees of unsaturation that we have. So it's going to give us a clue as to the structure of the molecule. For this scale, if you just substitute a chlorine for a hydrogen here, you can see that that basically is just a 1-to-1 substitution, right? Chlorine doesn't bond to anything else. So we're just going to treat the chlorine as if it were a hydrogen. If you add in an oxygen, oxygen doesn't affect the hydrogen deficiency index because when you add in an oxygen, you actually put another hydrogen on there, right? Oxygen is divalent. So the fact that it's divalent tells you that you have to put another hydrogen over here. So it's not going to change the number of hydrogens that we would expect either. Now, if you have a nitrogen, if you add in a nitrogen, that actually increases the number of expected hydrogen atoms by 1. So in other words, rather than oxygen, you know nitrogen is trivalent. So if you stick a nitrogen on the end of ethane rather than ethylamine, rather than a hydrogen, you get ethylamine, and then that leads on to 2 separate hydrogens there. So this is the formula that I use here, rather than like thinking about it in a complex way. Just know that you take 2, this is basically just going to tell you how many hydrogens are you missing? And so how many pi bonds do you have, right? So 2 times C plus 2, that's 2 times the number of carbons plus 2. That right there, that's the number of hydrogens you would expect for an alkane. Then you add nitrogen, right? Because every nitrogen should have 1 hydrogen with it. Subtract the number of hydrogens in the formula and subtract the number of alkanes, of halogens in the formula. Multiply all of that by 1/2, and that's going to tell you how many pi bonds and how many rings that you have. So you need to be able to do the hydrogen deficiency index to analyze these compounds. Okay, so that's that for mass spectrometry. Again, we're going to look at some data, and I'll show you exactly how to solve the mass spectrum in the next video, the combined spectroscopy video. But I wanted to cover the theory so you were familiar with the words like parent ion, the base peak, everything like that. All of that made sense before we move into how to use it all. Then I just wanted to summarize some important data from IR, hydrogen NMR, and then we'll look very briefly at carbon NMR before we call it quits for this little lecture addition down here. Okay, so remember that for the IR spectrum, we're going to focus on the diagnostic region. Anything below 1500 wave numbers is going to be what we call the fingerprint region. It's useful if we're trying to identify between 2 possible compounds. You can look at individual peaks and you have an unknown. You can look at individual peaks below 1500 and you should be able to kind of gauge, oh, this peak looks like it matches here. That's what we mean when we say fingerprint. You just literally compare them, one over the other. So, but we're going to focus on the diagnostic region. There's zone 1, which is 1600 to 1850 wave numbers. That's where we see the double bonds. 2100 to 2300 wave numbers. That's where we see triple bonds. 2700 to 4000 wave numbers. That's where we're going to find bonds to hydrogen. With each of those signals, what we're going to look for is the wave number. That tells us what type of bond it is. The intensity, how polar the bond is, generally speaking, or how many of that bond that you have as well as possible. And then the shape. So is it sharp or is it broad? A broad signal indicates hydrogen bonding or some kind of chemical exchange. Okay. And so this is kind of like our summary down here, right? So we know that we have bonds to hydrogen above 2700, triple bonds in the 2100 to 2300 region, and then we see double bonds 1600 to 1850. And then in particular up here, 2700 to 4000, this is where we see the bonds to hydrogen. These are very useful to like zoom in here. First off, one that's not shown here is the aldehyde. The aldehyde is going to show two different peaks, and I think it's at like 2750 and 2850, I want to say. Double check that in your book. It's not written down here, and I'm just remembering that from the top of my head, but it shows a distinct signal down here. Just keep that in mind. Now, from 2800 to 3000, that's where we see sp3 carbon hydrogen bonds. At 3100, we see sp2 carbon hydrogen bonds. At 3300, that's where we see sp carbon hydrogen bonds. Then amine peaks show up at like 3300 or 3400. They're tend to be a little weaker and just a little bit broad. And then we have OH peaks, whether that's carboxylic acids or alcohols. Alcohols are broad, but they'll show up from 3100 to 3500, generally speaking. If you have a carboxylic acid OH, then that's going to be extremely broad, and they can reach all the way down to like 2700, depending on that. So if you see a very, very, very broad peak in this region, it's a good indication that you have a carboxylic acid. Okay, next up, Proton NMR. So this is just a brief review how to analyze the Proton NMR spectrum. Remember that for each signal, you're going to consider the number of signals and the integration of those signals. If we already know the molecular formula, then we know the degree of unsaturation. The number of signals and their integration is going to give us a clue as to the symmetry. So for example, like let's say that we have a compound that we just figured out the molecular formula and we know it has 6 hydrogens. But when we look at the NMR, we see 2 signals, one that integrates to 1 and another that integrates to 2. Well, that wouldn't match with what we already knew about the compound unless you consider the fact that, oh, you can double it. If there's 2 protons that are chemically equivalent in the peak that integrates to 1, then that represents 2 protons, and then the peak that integrates to 2 would represent 4 protons. And that would work with what we already know about the molecule. And that tells you there's got to be some symmetry there in order to have those chemically equivalent protons. Okay, then you analyze each signal, and then you draw fragments with each signal. Keep in mind that when you analyze the signal, I guess I should have put this here. I wish I had. The things that are important is, of course, the chemical shift of the signal. That's going to tell you what the electronic environment of the NMR is going to look like. The multiplicity, in other words, the splitting. Is it a doublet? Well, the doublet has to be split by a neighboring proton, whether that's geminal or vicinal. That's something that you need to consider. Then once you have all of those fragments, you have something that represents each of those fragments. Try to assemble it and kind of piece it together into a complete structure that's consistent with what the data you have is. Now, if you do this after you've looked at the IR is going to tell you, a lot of the bonds that are possible. So this is going to analyze the IR is going to reduce the number of things you need to do analyzing the HNMR. And here's like a little table that kind of shows you where those chemical shifts are. So like a methyl group has a chemical shift of 0.9 parts per million, et cetera, et cetera. Remember the aryl region. This tends to be a place where things get a little messy. If your proton is bonded to a benzene ring, they tend to be multiplets, and they show up between 6.5 and 8 part per million. Now the good news is there's not much else there, so it's a pretty good indication that that's a aromatic region. Okay, now that was Proton NMR. Now the last thing that we want to learn about is carbon NMR. I know you're going over this in your lecture as well if you're taking the lecture at City College, but we want to talk about it here just very briefly because we are going to analyze them in this class. When you take a carbon 13 NMR, the signal that you're going to get is much, much weaker than what you get from a proton NMR. Proton is 99.99% of all hydrogen, so that proton shows up very strongly. But carbon 13 only accounts for 1% of all the carbon atoms. That's what we talked about before. So you need like a very sensitive receiver, or you need a very strong magnet, and you also may need a very concentrated NMR sample. And while with Proton NMR, we talked about shift, splitting, and integration, carbon-13 NMR, we reduce it. We're just looking at the chemical shift and then the number of signals that are involved in carbon-13 NMR. Now, the reason for that is because the splitting between protons and carbon-13 is extremely complicated. So if we were to look at that spectrum involving that splitting, you're not going to get any information out of it. So what we do is we decouple those. It's a really interesting thing. We don't have to go into it in depth here, but the idea is we're not going to worry about splitting when we look at carbon-13 NMR. It's like the pure, you can think of it as a way, like you don't have to worry about the magnetically active or the NMR active atoms that are bonded to each carbon-13, because it's just, we're going to decouple it. And it's interesting, like you just have to kind of shoot a different wavelength of light at it, and that like knocks down all the protons, but we don't have to talk about that here. You just have to know there's no splitting to take into account for carbon-13 NMR. Okay, now you can't take a proton NMR and a carbon-13 NMR at the exact same time because they have a different different amount of energy required. Remember, this is where you have like the alpha and beta state, so it takes a different amount of energy to make it resonate. So we still use the same standard, tetramethylsilane, TMS. This time though, looking at the carbons in the tetramethylsilane rather than the protons. And that carbon-13 NMR signal appears between 0 and 220 parts per million. Then what we want to keep in mind is the same thing that we talked about before with the chemically equivalent carbons, that all applies the same as what we talked about with chemically equivalent protons. So chemically equivalent protons, they're symmetrically reflective of one another in some way. The same thing is true with carbon-13 NMR. So like, for example, just to give you the easiest example I can think of, if you take a benzene ring, just a straight benzene ring, and you pluck it into your NMR, you see that you have 6 carbons there, but these 6 carbons, there's reflectant, there's reflection planes and rotational planes as well of symmetry. And what that means is basically each of these is going to show up at the same spot. So benzene is only going to have one signal when you put it in the carbon-13 NMR. Now, on the other hand, if you had a substituted benzene, like let's say that we had phenol. So phenol, now that's going to throw things off, right? So if we count up the different types of, if we look for symmetry now, what we're going to see is that there's a symmetry here, but that's it. So when we want to count the number of carbon-13 signals that we're going to see, well, we know that this is going to be 1, this is going to be 2, but this is chemically equivalent to this carbon over here, so that's going to be also showing up at 2. Same thing down here, 3 and 3. And then this one doesn't have anything chemically equivalent to it, so that's number 4. So phenol, we have 6 carbons, but we only see 4 signals when we look at its carbon-13 NMR. Yeah, so I guess I could have just gone to the next slide and kind of shown you here. So this is kind of interesting. This is a dimethyl benzene, which is also known as xylene, where you have 2 methyl groups. If you have this if they're ortho substituted, you get 4 signals. If they're meta substituted, you get 5 signals. And then if they're para substituted, you only get 3 signals. That's kind of an interesting way of kind of looking for the symmetry there. Now, finishing it up here, so that's how you know the symmetry of the molecule. The last piece of information that you can get is, the chemical environment. Just like with the proton signals, they can be shielded or de-shielded in the exact same way. sp3 carbons are between 0 and 50 parts per million. sp carbons are in the 50 to 100 parts per million range. sp2 carbons, and then also the benzene rings, that's from 100 to 150. And then finally, carbonyl carbons, that's from 150 to 220. So this is kind of like, you might want to like snap this table and have it available for when you need to analyze those carbon-13 NMRs. Okay, so I'll just briefly mention DEPT. We don't use it here at City College, but you may come across it in the future. So one thing that you can do is DEPT can tell you basically the number of hydrogen atoms that are attached to each of the carbons. So if you use DEPT 90, basically it's a different waveform that you shoot at the sample. If you use DEPT 90, you're only going to get carbons that are bonded to a hydrogen. If you use DEPT 135, you get CH3 and CH, that's positive signals, and then you see CH2 with the negative signals. The way it looks is basically, you just use the normal one, you get all of these, with positive peaks, then use a DEPT 90, well, that's going to show you specifically the CH peaks, then use that in conjunction with DEPT 135, the CH3s are positive, CH2s are negative, and CHs are positive. Okay, again, we're not going to use that. So what we're going to do is go ahead, look down below. There's a handout for you. That's going to be the how to solve combined spectroscopy problems. And then I'm going to have a video kind of narrating you and walking you through those problems. And then, once we're done, there will be a few sample exercises for you to do. And that's what we're going to focus on here in this first week. So that'll do it for this lecture, but I'll meet you here in a second once you've downloaded and taken a look at that how to solve combined spectroscopy problems handout. See you soon.